Okay, so today I'm going to give a talk on the incorrect logic for quantum programs. This is a collaborative work with Hoare and my supervisor, Nen Kunyu. So first, with the development of quantum device, we have a lot of quantum programming languages and platforms. And due to the counterintuitive in nature of quantum mechanics, so some programs written by professional experts can be erroneous sometimes. So for example, there used to be bugs in the example program in OpenOQSM, Qiskit, PyQuil. So the Hoare proposed a taxonomy for bugs based on the coding experience on scaffold. So now, generally, we have one method to deal with this problem. So that's the verification of the correctness of quantum programs. So this kind of programs, this kind of logic is designed for proving the absence of bugs in quantum programs. So for example, extend the classical Hoare logic into the quantum settings where he used the Hamiltonian or observed to work as a quantum predicate. And Joe limited that, and Joe in his work applied Hoare logic. He limited that the quantum predicates must be projection of subspace, and then construct a simplified proof rule. And of course, here we want to find bugs directly. So actually, we have some existing work about this problem. So for example, we have a dynamic assertion, so which basically need to perform the quantum element at runtime to detect errors. And another way to do this, use the statistical assertions. That means they will perform statistical tests over Lambo simulations of quantum programs. So these two works have some limitations. So first, they don't support bug finding ahead of time. So we hope to have a statistical logic. And another is this two existing work like sunless or complex arguments for their work. Okay, so now our work is majorly inspired by the classical incorrect logic proposed by Hoare in OOPSLA 20. So this logic is designed for finding bugs in classical programs. So now we have a problem. So how to extend the classical incorrect logic into quantum settings? So first, I want to introduce something about the incorrect logic. So here we define, give a program SP and a predicate P. So we define the post SP is the set of sigma prime, where the sigma prime is reachable from some space in predicate P. So in the left figure, the left side for nodes denotes the set of input states, and the rest for nodes denotes the set of outputs, and the arrows denotes the transition relation. So give a valid Hoare triple, we have the post SP is a subset of Q. So that means input satisfy P, then its corresponding output should satisfy Q. And also comparison in the incorrect logic, so we have the post SP includes the predicate Q. So that means every state in the post condition Q is reachable from some states in the predicate P. So that's the key point. So, and we can find that there exists a duality between these two kind of triples. So our problem is we want to extend it into quantum settings. So here we limited our discussions only about the projective predicates. So that means we use projection of subspace to a quantum predicate. Okay, so there are three major challenge problems. The first one, how should we characterize erroneous quantum programs without bringing any false positives? So in the classical settings, we use a set of erroneous states to do that. So can we do so in the quantum settings? So another one is about how to interpret quantum reachability. So we can say, so in the classical settings, we can say we reach every state in the post condition. So can we do the same thing in quantum world? And another thing is about the loop unrolling. So in practice, we will fix a bound for the loop unrolling in classical programs, but that would lead to the loss of completeness. So could this thing happen in the quantum world? So now we will figure these problems one by one. But before that, I would like to introduce something about the quantum predicates and quantum programs. So here, we just adopt the convention from applied Hoare logic or the dynamic assertion that use the projection to work as a predicate. So projection is a linear transformation from a vector space to the self such that the square of P equals itself. So here are some advantages of choosing predicate, projection as predicate. So first one, the satisfaction is a Boolean function, and it's easy to construct projection-based assertions, and it also contributes to have some simplified proof rules. So now we give some necessary definitions that we need in our following discussion. So give a semi-positive matrix A with its spectral decomposition. So we define the support of matrix A is a subspace spanned by vector psi I. And then we say quantum state rho, so that is a partial density matrix, satisfy a predicate P if the support of rho lies in the subspace P. So here is a projection P that maps the rho into P rho P that lies in the subspace P. So if we have rho satisfy the predicate P, then we would have P rho P equals rho. So that means the projection would have, won't have any side effects on the quantum states. Okay, so we also can define some logical operations on the predicate. So the negation of predicate P is the orthogonal complement of P. So that's the I minus P. I represents the whole subspace, and P and Q is the intersection of P and Q, and P or Q is a subspace spanned by the union of P and Q. So that is the space spanned by vectors in either P or Q. Okay. So now about the quantum program. So this is a small extension of the quantum well program. So we have the skip statement, sequence statement, and the initialization, the interval transformation, and the if and while statement. So here we use the quantum element to do the classical control here. So that's quite different from the classical programs since the quantum element will collapse the quantum states. And we also add an error statement here to represent all kinds of normal termination. And then we also adopt the assert statement I used before. So here we use the error statement and a projective quantum element to construct the assert statement. So if a state in the register Q bar satisfies the predicate P, so that means the assert statement will pass certainly without collapsing the state rho. But if not, so the assert statement may have a chance to enter the fourth branch and cause an error. So we will just exist abnormally. Okay. So now I want to introduce the semantics by an exact example. So here is the circuit for quantum teleportation. So we have 3 qubits here, and the input for the first qubit is a vector state psi, and we have a Bell state as the input for the rest of the 2 qubits, and it has 4 parts: a control node gate, a Hartmann gate, and two quantum element controlled Pauli gates on the third qubit. So the figure B is the corresponding program, and we add a assert statement at the end of the program. So that means if the output of the third qubit lies in the projection psi, so that means we got a right output. So here is the transition of quantum programs. So we start from the initial state, all times psi tensor product and the Bell state, and then we perform a CNOT gate, and then Hartmann gate, and then we do perform 2 quantum elements. So here, for example, we follow this branch. So M1, M2 equals 1, then we perform the logical NOT gate on the third qubit, and then M1 equals 0. So we do nothing we do nothing in the second element. So we can find that for each branch we all have output psi on the third qubit. So here we use S epsilon rho to denote the semantics, to denote the denotation semantics of our quantum program. So the label epsilon can be OK or errors. OK represent normal termination, and error represent abnormal termination. So here we just use here the SOK just represents the collection of all correct outputs, and we can sum them up together. So that would be all times psi. So if the program make a mistake, so for example, he misplaced the Pauli gates on the third qubit, so and we will find that we will get 2 different outputs on these 2 branches, and it would we have a chance to enter the fourth branch of the assert statement. So that would cause an error. So here we use the S error to represent the collection of these 2 erroneous outputs. So that's the formal definition of our semantics, denotation semantics. Okay, we will revisit them in the following slides. So now I'll go back to our previous questions. So these challenges. So the first challenge is how satisfaction of a projection is not precise. So here let me say some example. So the rho A represents the correct state 0, so colored by green, and the erroneous state rho E colored by red. So the mixture of these 2 states is still an erroneous state. So here we can use the satisfaction relation I have mentioned before to characterize this correct state. So that will be rho A satisfy PC. However, we cannot find a predicate QE such that the row satisfy QE without bringing false positive. Because if row satisfy QE, then we have the QE includes the subspace, the support of row. And since support row includes the PC, so we will get a contradiction that QE includes PC. So that is not what we want. So the contradiction comes from the fact that here we choose the projection as quantum predicates. So we don't have the following deduction that if the row does not satisfy predicate P, so we cannot say the row satisfies the negation of P. So that's a problem. So here we just choose to propose the under-approximated relation. So we will say rho is under-approximated by P if the support of rho includes the subspace P. So here we can just choose the QE to be the tensor product 1, 1, and then rho is under-approximated by QE. And we will find out that any kind of a mixture of rho C and rho E is still under-approximated by Q, and we don't bring false positive here. So that's that. The next question about how to interpret the quantum reachability. Here we also start from an example. So here we have a search statement. So for this search statement, for any input, we have at most 2 possible outputs. So that will be the correct output, 0, kid 1, and the erroneous output, kid 0. So we find that the state under-approximated by Q is a set of an infinite number of states, and we cannot reach every state under-approximated by projection Q. So that's a problem. So we can say we can reach every state approximated by a projection. So here, we choose to use the mixture of reachable state to avoid this problem. So give a valid incorrect triple PSQ, we will say that if achieves P, then the mixture of its reachable states after executing S will achieve Q. So here we can also define the post-SP to be the support of the mixture of reachable states. So that will be post-SP includes the subspace Q. So go back to this example here, we just choose Q equals 0, 0, and then this means achieving Q means it's possible to enter the fourth branch. So that's where we arrive at the erroneous states 0, okay? So now we just put this answers to these 2 problems together, and we get a table like this. So this is the comparison between the classical incorrect logic and our quantum incorrect triple. So the assertion in the classical settings, we use the set of states to deal with the assertion, and here we use the projection or subspace to do that. And in the incorrect logical, if sigma didn't pass the assertion, so we would say the sigma is element of the negation of P. So in the classical case, we say rho is under-approximated by Q. For some Q is not included in the P. And similarly, when we say a predicate is achieved in classical settings, we say the set of all reachable states should include the P. So here we just, and in the quantum setting, we say the mixture of all possible outputs is under-approximated by P. So that's the difference. Okay, so now we give the formal definition of our triple. Here, if an incorrect triple PSQ is holds, if and only if any rows support under-approximated by P, then the mixture of all possible reachable output states is under-approximated by Q. So the following the notational semantics of S row. So that's the collection of pairs rho prime n, where the n represents the number of distinguished transition chain that starts from the configuration S row and end up with the down arrow rho prime. And we use the sigma S row to represent the statistical sum of all output states. Okay, so and if we define the post-SP to be the support of the mixture of all reachable output states, so we have a similar duality between applied Hoare logic and applied quantum Hoare logic and our inference logic. So you can say for valid applied Hoare triple PSQ, we have post-SP is included in subspace Q, and for the incorrect triple, we have a reverse result. So now we introduce the proof rules. So we have atomic rules for the basic statements, so the empty, error, escape, entry, and initialization. And we also have the sequence rule and the order rule. Here, the subset relation denotes the relation between subspace rather than the set of states. And we also have the disjunction rule. So we use it to merge different triples. And as a comparison, in the applied Hoare logic or in the classical Hoare logic, we have the conjunction rule to do that. So And we also have the rules for the if structure and while program. So here we can see the difference between the classical programs and quantum programs. You can see the side effects of quantum elements on the states. So here with MM dagger instead of P itself. And here the Pn represents the unfold sequential composition of quantum element and the loop body S. And the capital N represents the number of loop unrolling. So we also have a derived rule for the assert statement. So just like the classical programs, we insert the assert statement at some place we are interested in. And if we find out that the post condition for the error case is non-zero, so that means we find a bug in the program. And we also get a theorem that our proof system is sound and complete. So that's all. And now we'll go back to our the third problem. So bounding iteration of loops may sacrifice completeness. So in the classical reasoning, so usually we need to fix a bound for the bound rule in practice. So here is the loop rule I have mentioned before. So we can do the same thing here. So but what happened to the completeness where we lose the completeness here? So actually, we won't do that. So here we have observation. We found that we can use the disjunction rule to combine the triples together, and we will get a bounded version like this. So for this bounded while rule, we find that the dimension of the logical warp support M0 P M0 dagger is naturally bounded by the dimension of H, and H is the state space of program S. So we can find that this desired post condition is increasing with respect to the subrelation as n grows, and we find that it won't change when n is larger than the dimension of H. So that's it. We can use this bounded version while rule, and we can still keep the completeness. Okay. So now I want to end my presentation with an example. That's the quantum teleportation I have mentioned before. So here we have two programs. The left side program is a correct program. So we start from the precondition. So that will be the psi tensor product, the Bell state, and then by applying our rule one by one, then we will get an empty post condition for the error case. And as a comparison, so in the right side, we just misplace the polling gate here, and we'll get a non-zero post condition for the error case. So that means we find a bug here. So now I like to give a summary of our work. So in this work, we just proposed the under-approximate relation to characterize erroneous states. So that will be if a state is under-approximate by P, then it means the support of rho is under-approximate by projection P. And we also define the incorrect triple based on the under-approximate relation. So that would be giving a valid triple PSQ. It means for any rows under-approximate by P, then the mixture of all reachable outputs is under-approximate by Q. And based on that, we have a sound and complete proof system. And we also use it to reasoning some examples about, for example, the group search, quantum teleportation, or RSS algorithm. So there are some major limitations of our future work about this. So the first problem is we may need a certain language for a general quantum predicate. So as you can find that in many similar quantum logics, we choose to use projections as quantum predicate. But to be honest, the projection is not that expressive enough. So we may need to find some well-structured quantum predicates in the future. So that's a big problem. And another one is that it cannot support the local reasoning. So you may find that the unitary rule in our work is just like you do the matrix multiplication. So you don't provide any speed up for that. So and this is a hard problem because in general you can't just decompose a big U. So we may need some quantum abstract interpretation here, so to make it more efficient. And we also don't consider quantum noise in our quantum power language. So that's all. So thank you. Okay. Sorry.
Thanks. Yeah. Oops. Where is it?
Here.
Oh, here. Thank you for the talk. I have right here a question for future work. So I'm very much an outsider, but you say you want to have more general assertions. And as far as I understood, like projections are nice because they don't destroy or they preserve correct states, right?
Yeah.
Do you have any idea how to generalize this without sacrificing this nice property of projections?
Sorry, can you just repeat your problem once more? I can't get your problem, so can you just speak it again?
So you said, so currently you use projections as predicates, right? And I'm very much an outsider, but I understood that projections are very nice because they preserve the correct states. They don't destroy them. You said in your future work you want to have more general assertions. Do you have any idea how to do this?
So, in fact, I have asked many times to my supervisor about this problem. So, do we have a well-structured predicate for quantum case? And he just answered, I don't know either. So maybe, and in his views, he thinks that if you choose a more complex quantum predicate, it's generally hard to verify them. So if you use a projection to construct the assertion, so if the state satisfies the projection, you won't collapse the states. But if you choose other kind of more complex predicates, you can't guarantee that. So this is the most important reason. That's why you see that many research about this topic, they only restrain their predicate to be projective. So that's the reason. So it's especially when you want to detect, you want to assert the assessment, you want to verify the assessment at runtime. You don't hope that the assertion will collapse the state, so you have to choose the projection. Yeah.
Hi, interesting talk. So I had a question about the loop put. You said it's like the worst case, it's bounded by the dimension of the Hilbert space, right? Like you're operating on?
Sorry, I don't get it.
Oh, sorry. For when you were arguing that like if you iterated the loop rule enough times, you argued it would terminate, right?
Mm.
And that was bounded by the dimension of the Hilbert space, right?
Yes,
Yeah. So yeah, we have a bounded version for the loop structure here, but in practice, the dimension of the space is still very narrow. So
I was going to say, because wouldn't that like grow exponentially with the number of bits, right?
So if you use the disjunction rule to combine on these triples, so I guess there is no such a problem.
Okay, but I guess what seemed weird here is so I've never actually looked at like using logic to verify quantum programs, but like I know like when you're dealing with like Hoare logic, it's often to talk about like loop invariance. Like if you're doing a proof by hand, if you could figure out like what that projected space was, like you have this seems like you're iteratively building up the loop invariant, right?
I'm sorry, I don't get your question.
So am I correct in thinking that this is like an algorithm to iteratively build up the loop invariant?
It's no loop invariant.
Okay.
It's no loop invariant.
Oh, okay.
You mean the invariance for the loop structure? Actually, we may find the invariance in some very special programs. For example, the iris program. So you can always find.
I might follow up online. So is it kind of like this, is this like the dual of what like a loop would like incorrectness logic? Is that like a dual notion to Hoare logic?
So the rule of that, if
okay.
I say well, it's one of the variant rather than an invariant.
Okay, a variant. Okay, that makes more sense then. Thank you.
Okay.
Thank you for your talk. Just want to confirm my understanding is that your white loop rules, this is correct, equivalent to the backward variant rules in incorrectness logic or not? That's your rules here. Because in backwards they have some variant predicate, and the rules there is include the termination. So I wonder that's because you say about the loop rules here, and you say about its loop rules, because in incorrectness logic we have the rules not bound and another rules we are allowed to bound. The rules, the backward variant rules, it include the termination already. So my question that this rule here, which corresponding to which rule in original incorrectness logic?
So are you talking about the termination program in the incorrectness logic?
No, because the rules in termination problem is different. Because the rules in incorrectness logic, the backward variant is including inside the rule is including, so that when you reach the post condition, so the loop must be terminated. So all the state there must be terminated. It's different to Hoare logic. The Hoare logic doesn't maybe terminate or not terminate, but because it's a reachability problem. So that's because I not quite understand that which one you talk about. You just confirm my understanding. Yes.
So generally speaking, here for this while rule, we don't require the termination of the while program. So we just guarantee that the predicate for some.
Sorry, I interrupt you. What's the PN here?
So you mean the capital N here?
Yeah, PN in the post condition, also PN in the premise.
Represent the result predicate for the unfold sequential composition of the quantum element and its nobody.
That is the variant.
Huh?
Is this the variant or?
That's not an invariant.
Variant, not invariant.
No, not invariant.
So what is this?
So that I guess that so basically this while rule is kind of trivial because it's just the result of the composition rule and the integral rule.
So that means composition. No, that means you say that you unroll the loops a few times, right? Yeah. And you get that one. Okay, yeah.
Yeah. So generally speaking, find the invariant for quantum while program is kind difficult. So maybe this is a particular example, iOS example. So you can find. So we can have a while program for this circuits, and you will find out if the output. So here maybe this is what you say here the R. So you can say in this program, if the outcome, if the measurement outcome is 1, so you continue the looping, and you will find that post condition for the circuit is always R. So this is a particular example. That's not the case for the general program.
Okay, yeah. Thank you. We are talking.
Thank you for the talk. One part I had a little bit of confusion on understanding was, for example, this example that you have on the slide. Could you get a bit of insight on how a developer or a verifier would come up with the incorrectness specification Q? And could you compare that with how hard it would be to come up with a correctness specification for the corresponding program if you were trying to verify it with IL, or not IL, regular Hoare logic, rather?
You mean which slide? Which slide?
So your last example slide, I think it was quantum teleportation, for example.
Yeah. Here. Could you just please repeat your problem?
Yeah. So for an example like this, I can kind of picture how if I wanted to use normal Hoare logic to prove the correctness, I would come up with the correctness specification at the end of the program. I was wondering if you could shed some insight on how to come up with the incorrectness specification of this program when you want to use incorrectness logic to detect a bug. How does one come up with a specification like this?
You mean using the ideas from classical incorrectness logic?
Well, not with anything in particular, just how did you come up with this example? How did you come up with the Q that was necessary for you to show the presence of a bug?
So I guess your problem is that you think that this bug is too artificial, or?
Well, no, I'm not making any judgment. I was just looking for understanding as to how you came up with it. I guess it was unclear. Okay. Yeah.
Okay. Sorry, I apologize for my poor English because I just get your problem not clear. So sorry about that.
So let's start the speak again.